Okay, section 2.1, day 2. We're going to wrap this up today. We left off going over frequency histograms and relative frequency histograms. We did not get to ogives. Yes, it looks like a G, or they use a G, but they actually use, when you pronounce it, you're supposed to use a J. So ogive, and then talk about the different shapes of distributions. Obviously, we got to interpret the graphs, and then dot plots should wrap this up. Okay. All right, so here we go. Let's go ahead and get to page 51. If you're home, you might want to do a quick read ahead of time if that helps you learn. But here we go. Let me explain these distribution shapes. Let's start with mound shapes. Okay. All right, I want you to write this description down here. Zoom in a little bit. This refers to a mound or bell-shaped distribution. These are also roughly symmetric. That's why it says mound-shaped and symmetric. They kind of have two concepts in that phrase. All right. So think like an anthill or a pitcher's mound or something like that. Something that looks to be symmetric as well. Or a bell. Okay, I recommend you also left some space over to the right to give some visual aids on these. So let's just say we had a histogram. That kind of comes first if you're writing this down. And a histogram kind of looks like this, where it's peaked in the middle, and then maybe it falls back off. And so if we were to kind of estimate that with a little curve, it kind of looks like a mound, right? Where the peak is in the middle, looks somewhat symmetric. They're not usually perfectly symmetric, but there's an example of what we'd call a bell-shaped distribution or mound-shaped distribution. Okay. All right, next one, uniform or rectangular. I usually call it uniform. So write this description down first. When each class of the distribution has equal frequency. The textbook says equal, but it's usually close to being equal or somewhat equal frequency. What would have a uniform distribution? Let me give you an example. Let's just say I had a six-sided die here and I started rolling it. So if I roll a six-sided dice, what would happen? Or die, right? Die's singular. So what would happen? Well, in the long run, all the outcomes are equal, right? So it would be uniform. Now, if I do a small sample, maybe the 6 happened a little more than the 5, so I might see a little up and down going on here. And that's why I don't really love the word just equal. Sometimes it's just close to being equal. That's a uniform distribution, okay? And you can see why also they might call it a rectangular. You see the rectangular box. Any questions on that one? All right, skewed distributions. Okay, here's the word description. Write this in. Leave some room for a couple pictures of it. A distribution in which one tail is stretched out longer than the other. The direction of skewness is on the side of the longer tail. Students early on will get this mixed up and call it skewed right when actually it's skewed left. So this is an important part of it here. The direction of skewness is on the side of the longer tail. All right, so number 10A from Friday's assignment is a perfect example of a skewed distribution. Remember, we had all the employees that were kind of over here. And then the company owner or CEO was way over here at 280,000. So the distribution, if I were to draw something to summarize that histogram, it would look like this. This is called skewed right. Where does the tail extend further? To the right. Some textbooks will call this positively skewed because it's towards the positive numbers on the number line, and then negatively skewed if the skewness happens towards the negative numbers. Okay? But we can also say skewed left or skewed right. So this would be a flip side. Maybe where would this happen? Maybe the last test scores, right? Most people did really well. All right. And then I had a few maybe outliers of people that bombed, something like that. So that would be a skewed left or negatively skewed distribution. Okay. All right. So I think we just got one more to cover. Bimodal. Now, bimodal in the past, mode usually means what occurred most often. So bimodal could mean there's two modes, but typically in statistics, it doesn't mean that. And it means we have two different distributions. Let's start with the explanation. I know there's a lot here. This is the majority of what we have to do today. All right, so I put in parentheses first, mound shape has one mode or unimodal, right? Because it's got a single peak up here, one mode. Bimodal usually has a separate peak. So when distributions have two distinct modes, this is usually because the data is from two different populations. All right, so here's my example. I don't know how detailed you want to get on this, or maybe just kind of summarize this real quick. Here's an example. Let's just say I had data on the heights of fourth grade boys and 12th grade boys, but you didn't know that ahead of time looking at the distribution. You'd see two different clusters. So typically we wouldn't want to put these together on the same number line or on the same graph, but sometimes distributions just appear this way, where you've got a cluster to the left of data, almost like a mound here, and then a separate mound over here. Okay, so that's bimodal. All right, so it kind of does mean two modes. Here's a mode over here, here's a mode over here, but careful, we don't usually call this bimodal. What I mean by that is let's just say this height actually was the same, and it was right there. We still kind of call that a single peak. That makes sense? So don't just look for the heights to be the same to call it bimodal. You want to look for two separate modes and two different clusters like that. Okay? Okay, to wrap this up, why don't you go ahead and read this critical thinking, and then we'll discuss it. So pause to do that. Okay, so the critical thinking is just a follow-up to what we just talked about. Fourth grade boys, 12th grade boys, let's just say we did height of seniors. You may think, okay, it's fine, one big distribution. Shouldn't be bimodal, but then if you look closer, maybe the male and female, we do see two different distributions because there's a difference there. All right, so another example of that situation. Okay, so if there are gaps in our histogram, like number 10A from the assignment, then it's going to probably include outliers. I know we didn't officially discuss that before, but usually that phrase is just a common sense phrase that we use in our everyday language. So here's the technical definition here, okay? Outliers in a data set are the data values that are very different from other measurements in the data set. Data values that are very different from other measures in the data set. It just doesn't really fit. It's not typical of what we'd see in the distribution. Okay, what you doing writing that down? I'll go ahead and pause this. I'll let you read this to yourself and then fill in these definitions. And then we'll take a look at an ogive on page 53. Okay, pause at home to do that. Okay, so as you just saw, an ogive. Yes, ogive. There's how you're supposed to pronounce it. All right, just kind of builds up a little cumulative or running tally of what's going on. So this was the daily high temperatures for Aspen, Colorado. How many times was the daily high between 10.5 and 20.5 degrees? 23. Okay, so you're gonna have to create one of these ogives in your OTI today. So all you have to do, you always start at the lower limit down here, just like you would a histogram. How would we start a histogram? Doing the same thing on this x-axis, the temperature. So instead of a bar, you kind of draw a line to that height of 23. Okay, but then it starts to accumulate. Where a histogram would only have a height of 43 now, right? So it would be a bar here. But now you take the 23 and the 43, and what do we get when we add those together? 66. So at 30.5, now we're at 66. So how do you read this? Basically what that means, 66 days were 30 and a half degrees or lower, right? That's how we can interpret that. How do I get this next number of 117? Add all three of these up, right? Or add the 51 to the 66, and I get to 117. So now that means 117 days, the temperature is below 40 degrees if I'm summarizing all this. All right, it kind of shows you the rate of change too of what's going on. Right at the very end, there's not much change. There weren't many days that were between 50 and a half and 60 and a half degrees. Okay, or 51 to 60 degrees. So in the end, basically this last number should equal the total of 151. Okay, now sometimes they don't label these dots, and all you got to do is just kind of estimate it the best you can. Like it tells you 117, but if they ask you to read it and it's not there, you just go up and you go across, and somewhere, people are going to say 118, maybe 119, and that's okay if it's an estimation. Does that make sense? So sometimes you just use these to estimate. Okay, they may even say, what do you think the temperature was when they had 80 days? So you'd go across to 80 to this line and go down. Okay, and that temperature that corresponds to it's around 32 degrees. Okay. All right, so there's an ogive, and like I said, we'll have a chance to follow up with that in the OTI and get some more experience with that. Okay, last thing I'll cover here today is a dot plot. Dot plots come up here. They go over it on page 61 a little bit, but I'll just give you a real basic example. So you've got one in the book, and then one we'll put in our notes here, okay? Here's what a dot plot does. Why don't you write this explanation here at the bottom of the notes in this blank area. This reads, dot plots, you plot data values with a dot above the corresponding value on the horizontal axis. Plot data values with a dot above the corresponding value on the horizontal axis. Stack repeated values. Pause as you're writing that down. You've done this before. Maybe it's just been a while. My kids from Hill Elementary come home and have to do some of these dot plots. So you've done it. It's easy. So let's just do a real basic example so you can get it going. Let's just say I've got a collection of test scores, okay? Like this. All right, so you just kind of create a number line. You look at your range of values to get something suitable. 80 to 100 is all I need, so I'm just going to go every 5, 80, 85, 90, 95, 100. Try to space it out evenly on your scale, and then just put your data down here, right? These are test scores. All right, so as we do, 90. So I'm going to cross that out. I'm going to put a dot above 90 right there. I go on to 95. I have two of them. So at 95, and if I have a repeated one, we stack repeated values like that. Just make your dots kind of noticeable, right? Make them big. 85 happened here. 80, 90, and 100. Okay, so that's called a dot plot. Okay, and that's it for section 2.1. So today's assignment will focus on some of these new materials along with day one's materials, and then we'll do 2.3 tomorrow, which is just one learning target, 2.3.